The universe started in complete darkness, perfect darkness. For hundreds of millions of years, there were no stars, nothing, just this endless, cold sea of gas. Silent, that period is called the Cosmic Dark Ages. It's the time between the Big Bang's afterglow fading and the first starlight finally appearing. That era of total blackout is what set the stage for everything. Every galaxy, every planet, all the starlight we see now, it all started there, and we want to know how gravity worked when it was totally secret. What the first matter even looked like, and why astronomers are trying to listen for a whisper from that ancient void. What does a universe feel like when it's just waiting to be born? The universe was just potential at that point, a blank canvas. To get a sense of the Dark Ages, you have to think about the timeline. The Big Bang happens, that initial flash. And then things settle. What's left is this warm glow, the cosmic microwave background. That light gets released about 380,000 years in. That's really the starting point. The curtain opens on the Dark Ages right there. From that moment, for the next 100 million years, maybe 200 million, the cosmos goes quiet. Profoundly silent, but it wasn't empty. All the ingredients were already there, spread out. A simple fog, hydrogen and helium gas, neutral, just hanging in the dark. And this darkness, it's a specific kind. It's not like a cloudy night. It's a total blackout, no stars, no galaxies, nothing that could turn on a light. All the raw material for creation was just sitting there, perfect stillness. That's the challenge now. How do you study an era that produced no light? No light to travel to us. The nature of the Dark Ages makes it one of the hardest periods to observe. We have to piece it together from clues, listening for echoes in the darkness that came after. That quiet wasn't a peaceful one. It was more like the stillness after something huge. To get the Dark Ages, you have to go back to what was happening just before. The universe started as pure, chaotic energy. For hundreds of thousands of years, it was this searing plasma, a thick soup of particles, protons and electrons, all charged, constantly smashing into the intense light that was everywhere. It was a fog, so dense light couldn't travel far before it got scattered again. The cosmos was opaque, a brilliant, roiling fireball. Then there was a shift. The universe expanded and it cooled. At about 380,000 years old, it hit a critical temperature, recombination. The energy dropped low enough that electrons could finally be captured by protons. They combined, they formed the first atoms, neutral hydrogen atoms. It's a simple name for something that changed everything. Like a dense, steamy fog suddenly clearing. That plasma fog had trapped all the light for eons, but the instant those neutral atoms formed, the fog lifted. The universe became transparent for the first time. That light that was liberated, we see it now as the cosmic microwave background. It's the ancient snapshot of that moment, the afterglow of creation, stretched and cooled into this faint microwave whisper. But for the universe, the consequence was deep. With the fog gone, the landscape was revealed, and what was there? An unimaginably vast, empty expanse. A sea of simple, neutral hydrogen gas stretching in every direction. The blinding brightness was gone. In its place was this profound, unbroken darkness. That's the true starting line. The stage was set, the actors were in place, but the curtain was still down. The long, quiet era of darkness could begin. And in that new, transparent void, a question hangs. What tiny seeds of structure were already hiding in that gas? What faint ripples from the Big Bang, waiting for gravity to find them? This new darkness wasn't empty. It was full of possibility, and it was made of something very simple. Just three things. Most of it, about 75%, was hydrogen. A proton and an electron, then helium, almost all the rest, around 25%, and then just traces of lithium, that's all. No carbon, no oxygen, no iron. Nothing that would later make planets or life. It was just this soup of the lightest stuff, cooling in the dark. But that visible recipe misses the main ingredient, the one you couldn't see. Woven through all that hydrogen and helium was dark matter. It didn't give off light or reflect it. It was invisible, but it had mass, so it had gravity. And while the gas just drifted, the dark matter was already doing something. It was starting to respond to those faint ripples from the Big Bang, those little whispers of density in space. And under its own gravity, the dark matter began to clump, slowly. It began forming a skeleton, a vast, invisible framework of wells and tendrils. That's the silent construction of the Dark Ages. You could think of the hydrogen and helium gas as a kind of cosmic flesh. It was everywhere but diffuse, and the dark matter was the bones, the scaffolding forming underneath. The gravity from those clumps of dark matter began to pull on the gas. It created places where the gas would naturally flow into those deepening valleys. So the stage was being set, a collaboration between an invisible architect and a visible but dormant material, and for millions of years this went on in total blackness. The skeleton got stronger, its pull more defined, while the gas just waited, dark and neutral. The central mystery is in that interplay. How did that invisible framework guide the first gatherings of light? And when would the gas finally respond, not with a slow drift, but with a flash of fire? It wasn't just dark because there was no light. The universe itself was in that state. For light to exist, to travel, you need something to create it, a source, and in the Dark Ages there were no sources, no stars, no galaxies. Nothing was hot enough, dense enough to start burning. Every light was off. There was still a glow everywhere, the cosmic microwave background. But that light had been stretching for hundreds of millions of years, cooling down from visible light into microwaves. We can't see microwaves, so even with that energy everywhere, the sky would have been completely black, a void. But it's more than just no sources. Say a single photon was made. It wouldn't have gone far. The universe was full of that neutral hydrogen gas, and neutral hydrogen absorbs the specific light that stars make. It's like a fog, a thick cosmic fog that soaks up that exact color. Any spark would have been swallowed immediately, a blanket smothering any light, so the darkness was absolute for two reasons: no fire to start, and an environment that snuffed out any ember. For light to win, something had to change the gas itself. It had to rip the electrons away, to reionize the hydrogen, to clear the fog. That task would fall to the first stars. Gravity was the one thing still working. Everything else was quiet, but gravity had a plan. It had these instructions, faint ones, left over from the very beginning. Those quantum ripples from the Big Bang, frozen into the background radiation, just whispers, but gravity listened. Over millions of years, it made those whispers louder. It started pulling on mass, and the two main ingredients, they acted differently. There was the ordinary gas, hydrogen and helium, and there was the dark matter. The dark matter was the key. It didn't interact with light, so nothing pushed it. It just felt gravity, so it clumped first. It flowed into those ripples, made them deeper. It built this invisible skeleton, a network of filaments and knots, all dark matter, stretching out. Where those filaments crossed, the dark matter gathered into halos. Spherical clouds with a strong gravitational pull at their center. Those were the construction sites. Then the ordinary gas, the hydrogen, started to notice. It had been drifting, but now it felt that pull from the halos. Slowly, the neutral hydrogen began to flow inward, a silent river moving along the dark matter filaments, pooling at the hubs. Like a valley filling with a dark mist drawn by a magnet you can't see. This wasn't fast, it was slow, an accumulation over eons, but with every atom that fell in, that core of gas got denser. And warmer, the stage was being set. Gravity was the director, using an invisible scaffold to gather the materials. It was preparing the nurseries, the cradles. Where the first sparks would finally catch. What would it take for that gas to ignite? The seeds had to come from somewhere. That's the first mystery. The universe didn't start smooth. If it had been perfectly smooth, gravity would have had nothing to grab onto. The gas would have just stayed a fog. But it wasn't smooth. It had these tiny differences. Some patches of that early gas were just a little denser than others. Think of a field of soil, mostly level, but if you look close, you see little mounds and dips. Those are the seeds. In the cosmic field, those denser patches had a bit more mass, and that made all the difference. Gravity is drawn to mass, so over the dark ages, gravity pulled on those dense patches. The extra mass acted like an anchor. More gas from around it would drift in, making the patch even denser. It was a silent feedback loop, a seed gathering material in the dark. But the question is, why were those seeds there? What planted them? To answer that, you look at the oldest picture we have, the cosmic microwave background. That faint glow from when the universe became transparent, it's not perfectly even. It has a pattern, a texture of tiny temperature differences, warmer spots, cooler spots. And those spots are the direct imprint of those density seeds. A warmer spot in that ancient light means a slightly denser region back then, a place where matter was packed a bit tighter. Cosmologists study this pattern like a map. It's the original blueprint, frozen from when the universe was 380,000 years old. Every galaxy cluster, every cosmic void we see now traces back to one of those tiny temperature variations. So figuring out the exact nature of these seeds is a huge pursuit. Were they planted by quantum fluctuations, stretched to cosmic size? The pattern holds the clues. It tells us how much matter was there, how it was distributed. It gives us the starting conditions for the entire dark era that followed. It's the first chapter. Written in a language of faint heat and cold, waiting for gravity to read it aloud and start building in the dark. That blueprint of seeds in the cosmic background, that faint pattern, was the starting point. And the primary builder was something we can't see, dark matter. As the dark ages went on, those tiny density seeds began to grow. Gravity pulled, and dark matter, unaffected by light, was the first to respond. It started to collapse into structures. We call them dark matter halos, vast spherical clouds of this invisible stuff, held together by their own gravity. They were the cosmic cradles, the foundational pits where the first stars would be born. They weren't all the same. The smallest ones, the very first to likely form, are called mini-halos. They might have had the mass of only a few thousand suns, maybe even less. These were the pioneers, tiny gravitational wells, the first places where matter really began to gather. But their formation wasn't random. They followed a map, an architecture being drawn by the dark matter itself, the cosmic web, that invisible skeleton of filaments and knots. Dark matter flows along vast highways in space, intersecting at dense nodes. The first halos formed along these lines. Mini-halos appeared like beads on a string, tracing the faintest threads. Over time, through hierarchical structure formation, these small halos did something. They began to merge. Gravity pulled them together. Two mini-halos would find each other, collide, combine into a larger halo. Then that larger halo would attract others. It was a slow game of accumulation, building ever more massive gravitational anchors over millions of years. This merging is critical because the size of the halo determined what happened next inside it. A tiny mini-halo might pull in some gas, but its gravity might be too weak to compress that gas enough to ignite a star. It might just sit there, a dark, silent knot, but as halos merged and grew, their gravitational pull became stronger. They became deeper wells, and that's when they could start to efficiently funnel ordinary hydrogen gas into their cores. The gas flowing along those same dark matter filaments would drain into these deepening pits. As it fell, it compressed, it heated up. This sets the stage for the final question of the Dark Ages. When was a halo massive enough? When was its core of gas dense and hot enough to cross the threshold, to trigger the nuclear fusion that would end the darkness? That timeline from the first mini-halo to the first star is what the most sophisticated computer simulations are trying to solve. They take those initial seeds, the laws of physics, and let the universe run in fast forward inside a supercomputer. Watching to see which halo wins the race and what that first flash of light finally looks like. The gas was a puzzle. It wasn't just hydrogen and helium sitting there. It was a dynamic substance with its own rules. And those rules were different from the ones that govern star formation today. That's the third mystery, the behavior of the primordial gas. Its physical state held the key. Because how that gas behaved, how it cooled and collapsed, would dictate not just when the first stars lit up, but what those stars were like. Their size, their brilliance, their nature was written in the physics of that simple fog. Now today, when a gas cloud in our galaxy starts to collapse under gravity, it has a way to shed energy. It can cool down, and cooling is essential. For a cloud to keep collapsing into a dense star, it has to lose the heat that builds up from the pressure of its own collapse. If it stays too hot, the gas pressure pushes back and the collapse stalls. Modern clouds cool efficiently. They're laced with heavy elements, dust grains, complex molecules. They act like a radiator system, letting the cloud release heat into space and shrink further. But the first gas clouds had none of that. No carbon, no oxygen, no dust, just hydrogen and helium atoms. Their toolkit for cooling was incredibly limited. So how did it cool? The primary mechanism was molecular hydrogen. Not single atoms, but two hydrogen atoms bonded together into a simple molecule. In the depths of those collapsing dark matter halos, where densities were rising, these H2 molecules could form. And when they did, they could do something special. When they vibrated or rotated, they could emit a tiny amount of infrared radiation. That was the escape valve. That faint glow was the only way for these primordial clouds to shed their gravitational energy and keep collapsing. But it was a slow, inefficient process compared to what happens now. Think of trying to cool a hot engine by blowing on it with your breath versus having a full liquid cooling system. That's the difference. The first clouds had to rely on that slow molecular breath. This slow cooling rate had a profound consequence. It set a minimum size for the first stars. Because the gas couldn't cool quickly, it couldn't fragment into many small, dense clumps. Instead, the entire inflow of gas into a dark matter halo tended to funnel toward a single, massive core. The physics pushed it to build something big. Without efficient cooling, the gas stayed relatively hot and puffy, resisting collapse until an enormous amount of it had gathered. Only then would the gravitational pull be overwhelming enough to force it inward despite the heat. So the dynamics of this pristine gas, how it flowed and clumped and resisted, wasn't just an academic detail. It was the factory setting for the universe's first factories. It meant the very first stars were likely not like our sun. They were probably behemoths, monsters, hundreds of times more massive, burning ferociously bright and blue and living very short lives. Their behavior, dictated by the simple, stubborn physics of hydrogen, would then go on to change the universe all over again. Their explosive deaths would seed space with the first heavy elements, ending the era of pristine gas forever. But that first ignition, that first flash, was waiting on a simple question. Could enough molecular hydrogen form in time, in the right place, to cool a cloud and let gravity finally win? That first molecule of hydrogen, it was a delicate thing, an improbable event. In a universe with no solid surfaces, no dust grains to stand on, two lone atoms had to find each other. And bond, this quiet chemistry had to happen before any fire could ignite. The universe was learning a new trick, and it was essential. Without it, the gas clouds would have stayed too hot, too puffy to collapse. So the story of molecular hydrogen, H2, is really the story of the universe finding an off switch for heat. But how did it happen? The process was slow, incredibly inefficient at first. In the diffuse gas of the early dark ages, hydrogen atoms were mostly solitary. For two to form a molecule, they needed a third party, something to carry away the excess energy of their bond. Otherwise, they'd just bounce apart. One pathway was a rare three-body collision. Two atoms come together, and at almost the same instant, a third collides with them, absorbs the energy, lets the first two stick. But these precise triple meetings were very uncommon. In that thin gas, the other main pathway was more subtle. It involved the only other particles floating around, the leftover free electrons and protons. A free electron could attach itself temporarily to a hydrogen atom, forming a short-lived negative ion that gave the atom a slightly different character, made it more likely to attract a second, regular hydrogen atom. When they bonded, the extra electron was released, taking the energy with it. This process, though still slow, was likely the dominant way. The very first traces of molecular hydrogen formed in the darkest, emptiest regions. This wasn't fast chemistry or robust. It was a faint, fragile network beginning to stitch itself together within the deepening wells of dark matter halos. As gas pooled there, density increased, making these interactions slightly more frequent. A tiny fraction of the gas, maybe 1 part in 10,000, slowly converted from atomic to molecular form. But that tiny fraction was enough, because molecular hydrogen has a special property. When it gets jostled and heated in a collapsing cloud, it can release that energy by vibrating and rotating, emitting a faint whisper of infrared light. This infrared glow could escape the cloud, carrying thermal energy away into space. That glow was the universe's first cooling system, a cosmic thermostat. A gas cloud contracts under gravity. It heats up, that heat creates pressure, fights against further collapse. But if the cloud contains even a little H2, that molecule can glow, the cloud can cool, internal pressure drops, and gravity can win again, pulling the cloud tighter. This cycle, contraction, heating, cooling, and further contraction, that was the engine of the first star formation. The efficiency of this early chemistry set the pace. How quickly could H2 form? How effectively could it cool the gas? The answers determined how massive the first collapsing cores would become, a subtle process with monumental consequences. This fragile molecule, forged in the void through improbable meetings, became the architect of structure. By allowing gas to condense, it handed gravity the final tool it needed to sculpt the first luminous objects. The Dark Ages weren't just a time of gathering mass, but of learning to manage energy, and the first lesson was written in that quiet bond between two hydrogen atoms. The universe was learning to cool itself, molecule by molecule. But the question is, how long did that take? That's the fifth mystery. A great unknown. When did the first light finally break through? We have estimates, a broad window. The first stars probably ignited somewhere between 100 and 200 million years after the Big Bang. But 100 million years is a long time. Was it early in that window, or was it late? And was it a single event, or was it a slow dawning? The answer isn't just a date. It's a story about how the cosmos woke up. Think of a dark landscape before sunrise. The first light doesn't appear everywhere at once. A mountain peak catches the sun long before the valley below. The cosmic dawn likely worked the same way. Some regions of the early universe were slightly denser. Their dark matter halos formed sooner. Their molecular hydrogen chemistry kicked in faster. These became the mountain peaks, the first places to glow. other regions, quieter and more diffuse, might have lingered in darkness for tens of millions of years longer. So there wasn't one moment the universe turned on. It was a patchwork awakening. What decided who was first? A few factors. The local density of dark matter was a primary driver. Where that invisible skeleton was thickest, gravity worked fastest. It pulled gas into deep wells more efficiently. The prevalence of molecular hydrogen was another. In some halos, the delicate process of H2 formation might have been more successful. That let the gas cool and collapse rapidly. In others, it might have been stifled. That delayed star birth, and then there are the wild cards, like the possible influence of early black holes, not the supermassive ones at galaxy centers. Smaller, primordial ones, they might have formed from extreme density in the very early universe. If such an object existed in a halo, its fierce gravity could have gobbled up gas. Heated the surroundings that could disrupt star formation, or maybe even accelerate it in a chaotic whirl. The timeline wasn't a simple countdown, it was a local competition. Influenced by subtle variations written into the fabric of space from the beginning. This is why pinpointing the timeline is a primary goal for the next generation of observatories. Telescopes like the James Webb Space Telescope peer deep into the past. They hunt for the earliest galaxies, but to probe the era before those galaxies, the true dark ages, we need a different kind of eye. Astronomers are building instruments to listen. They're searching for a specific, faint signal, the 21-centimeter line from neutral hydrogen. As the first stars and galaxies began to shine, their intense ultraviolet radiation started to heat and ionize the hydrogen fog around them. This process changed the characteristic signature of that hydrogen in radio waves. By mapping this change across the sky, scientists hope to create a movie of reionization, a chronological map showing how and when the cosmic fog lifted in different regions. It would be the ultimate history of the dawn. Finding that signal is like trying to hear a whisper across the ocean during a storm. It's incredibly faint. Buried under interference from our own galaxy and modern radio signals. But the hunt is on, because locked within that whisper is the answer to when our story truly began. When the long night ended and the first chapter of light was written, that faint whisper from hydrogen, it has a deeper rhythm, an echo. To understand where the first stars were born, you listen for a cosmic vibration. Frozen in time, it's called a Baryon acoustic oscillation. The name is complex, but the idea is powerful. It's a fossilized sound wave from the universe's first moments. A single note stretched across the cosmos. Before the Dark Ages, the universe was that searing plasma, a thick soup, light and charged particles. In that dense, hot fluid, gravity tried to pull matter together. But the radiation pressure pushed back. That created a tug of war, a pressure wave like a sound wave moving through air. These waves rippled outward. From every slightly denser region, for hundreds of thousands of years they traveled, a sphere of compressed matter and radiation, expanding at a significant fraction of the speed of light. Then, at recombination, the music stopped, the fog cleared. The universe became transparent, the light raced away. That became the cosmic microwave background. And the matter, now neutral atoms, was left behind, frozen in place, at the exact edge of where those sound waves had traveled. Imagine dropping a pebble into a pond. And the pond instantly turns to ice. The ripples are frozen solid. That's what happened on a cosmic scale. The result is a subtle pattern in how matter is distributed. If you could map all the galaxies today, you'd find they're slightly more likely to be separated by a specific, vast distance. That distance is the radius of that frozen sound wave. It's a standard ruler etched into the fabric of space. Astronomers use this ruler to measure how the universe has expanded. By seeing how this standard distance appears at different eras, they trace the history of cosmic growth. But for the Dark Ages, this oscillation is more than a ruler. It's a sonic blueprint. That frozen wave pattern was imprinted on the neutral hydrogen gas. So the gas wasn't randomly scattered. It had a faint, rhythmic texture, a vast three-dimensional honeycomb, slightly denser walls and emptier voids. All set to that primordial scale. When gravity began its work, it didn't start from a blank slate. It worked on this pre-patterned material. The first dark matter halos, and thus the first stars, didn't form just anywhere. They were more likely to coalesce within those walls, along the ghostly imprint of that ancient sound. So by studying these baryon acoustic oscillations, we aren't just measuring the universe. We're reconstructing the large-scale environment of the nursery. We're listening to the echo of the Big Bang to understand the stage upon which the first light would eventually appear. It tells us the first structures weren't isolated accidents. They were part of a grand, rhythmic architecture, born from a vibration that has been ringing for over 13 billion years. We can't see that time, but we can build it. In these huge digital labs, scientists are reconstructing the Dark Ages from the ground up. This is computational astrophysics. The most powerful supercomputers we have, running the universe in fast forward. It's our only window, a window into a time before light. You start with a simple set of ingredients. The laws of physics, gravity, hydrodynamics, thermodynamics, and the initial conditions. Those tiny density seeds we see frozen in the cosmic microwave background. You feed that recipe into the machine, then you press start, and for months, sometimes years, the computer calculates. It tracks trillions of particles. Dark matter and gas across a virtual volume of space. It simulates hundreds of millions of years in a fraction of the time you watch gravity work. Dark matter particles begin to trace out the filaments, the cosmic web. Where those filaments cross, halos start to form. They grow from mini-halos into massive structures. Through mergers and inside those halos, the gas follows. It flows along that invisible scaffolding. It pools at the centers. The simulations model the chemistry. Molecular hydrogen formation. They calculate how that molecule cools the gas, lets it condense further, and you see it, the birth of the first collapsing core. A single, dense knot, pristine hydrogen and helium, growing hotter under its own weight, until it crosses a threshold. Nuclear fusion ignites and a star is born. These virtual universes aren't just animations, they're experiments. By tweaking the parameters, scientists can ask questions. What if dark matter behaved differently? What if the primordial gas had a different composition? They can test theories about the size of the first stars, whether they formed alone or in clusters. How their fierce radiation began to eat away at the hydrogen fog. And most importantly, the simulations show the feedback. That first star lives a short, violent life. It ends in a colossal supernova. The simulation tracks the explosion. It watches as it blasts heavy elements back into space, sends shock waves through the surrounding gas. That feedback can trigger new star formation nearby, or it can sterilize a region, delay further growth for eons. It's a dynamic story, a chaotic story. These digital laboratories are just starting to unravel it. They offer a glimpse, a hypothesis written in light and data, of how the long night finally ended. And every new simulation gets us closer to answering the question, what did the universe look like the moment it woke up? The simulations give us a theory. A digital hypothesis, but science needs evidence, a real signal from the void, and that evidence might be the faintest whisper in all of astronomy, a radio hum from the hydrogen atoms that filled the Dark Ages. This is the hunt for the 21-centimeter line, the sound of the universe before it was loud. Every neutral hydrogen atom is a tiny radio transmitter. Deep inside, the spin of its single proton and its single electron can align in two ways, parallel or anti-parallel. and these two states have a minuscule difference in energy. Once in a great while, an atom in the higher energy state will spontaneously flip. It drops to the lower state, and when it does, it releases that tiny bit of energy as a photon. A radio wave with a wavelength of exactly 21 centimeters. For a single atom, this flip is incredibly rare. It might happen once every 10 million years. But the Dark Ages universe was filled with uncountable sextillions of these atoms, so that rare event was happening everywhere all the time. It created a pervasive radio glow. Incredibly faint, a signature woven into the fabric of space itself, and this signal is not static. It changes with the environment. During the Dark Ages, the hydrogen gas was bathed in the warmth of the cosmic microwave background. The atoms absorbed and re-emitted this 21-centimeter radiation. But as the first structures formed, things shifted. In regions where dark matter halos were pulling gas together, the density increased. This made the hydrogen atoms collide more often, and those collisions could flip the spins, pumping more atoms into the higher energy state. This made the gas appear to glow brighter in the 21-centimeter line against the cosmic background. Later, as the first stars and galaxies ignited, their fierce ultraviolet radiation did something else. It began to heat the hydrogen fog, and warm gas emits a stronger 21-centimeter signal. So astronomers predict a timeline written in this radio whisper. First, a period where the signal grows stronger as gas gathers and is excited by collisions. Then, a turning point as the first starlight heats the gas, causing another shift in the signal's character. And finally, the signal would vanish entirely in regions where that starlight ripped the electrons away, ionizing the hydrogen and shutting off the 21-centimeter line for good. By carefully tuning our radio telescopes to different frequencies, we can listen to different slices of time. Lower frequencies correspond to signals from deeper in the past. The goal is to map this signal across a vast range of frequencies, to assemble a three-dimensional movie of the cosmos. From the deep, neutral darkness through the first stirrings of structure to the blazing dawn of reionization, it would be the ultimate documentary. Filmed by the hydrogen itself, but the challenge is monumental. This primordial signal is extraordinarily faint. It is buried under a roar of foreground noise. Radio emissions from our own galaxy, from Earth's atmosphere, even from our own civilization. Separating that cosmic whisper from the terrestrial shout is like trying to hear a single snowflake land in the middle of a hurricane. It requires telescopes in some of the most remote places on Earth, in deserts and polar regions, and it requires a new generation of instruments designed not as single dishes, but as vast arrays of simple antennas. They work together to filter out the noise and isolate the signal. Projects like the Hydrogen Epoch of Reionization Array and the future Square Kilometre Array are built for this singular purpose. To listen for the birth of light. If they succeed, they will not just give us a date, they will give us a map showing us where the first stars flickered on, how their influence spread, and how the cosmic fog was finally, irrevocably burned away. The signal from the Dark Ages is incredibly faint, and it's buried. There's a wall of noise that drowns it out. That noise comes from everywhere. First, our own galaxy. The Milky Way is a bright source of radio waves. From dead stars, from magnetic fields in the dust, it creates this constant, bright foreground, a radio fog over the whole sky, then the Earth's atmosphere. It crackles with its own radio noise, and then there's us, our civilization. Cell phone towers, television broadcasts, satellites, they all leak radio waves into space. This human interference creates a thicket of noise, a digital jungle. The ancient signal has to penetrate that. Separating that primordial hum from the cacophony is the ultimate challenge. It's not a needle in a haystack. It's like trying to hear one specific note from a single violin from miles away. while you're standing in the front row of a heavy metal concert. The signal is millions of times weaker than the noise around it. You can't just build a bigger radio dish. A bigger dish would collect more of everything. More of the symphony and more of the roar. It would make it worse, so astronomers have to be clever. They have to listen in a different way. That's why projects like the Hydrogen Epoch of Reionization Array, the future Square Kilometre Array, they aren't traditional telescopes. They're vast fields of simple antennas spread across kilometers of remote land, in places like the high desert of South Africa or the outback of Western Australia. These places are chosen for their radio silence, far from the electronic chatter of cities. These arrays listen to the entire sky at once. They don't focus on one point. They collect an ocean of radio data, every frequency from every direction. Then, with immense computing power, they start the work of subtraction. They build detailed models of all the foreground noise. The galactic symphony, they map its brightness, its polarization, how it changes with frequency, and they subtract this model from the total signal, layer by layer. Hoping that what remains after all the known noise is gone is that faint primordial hum. This process needs more than technology. It needs profound patience. A single observation can last for years, collecting petabytes of data. The analysis is iterative. You make a model, subtract it, see what's left. You look for artifacts, for errors. You refine, you start again. It's a slow, meticulous archaeology, digging down through strata of interference to find the oldest layer. A mistake, a subtle misunderstanding of the foreground, can create a false signal. An echo of our own world mistaken for a whisper from the dawn. This work is a testament to human ingenuity, a quiet, persistent effort to hear a story waiting over 13 billion years to be told. The challenge isn't just to detect the signal, it's to trust that what you finally heard after all that filtering and waiting is truly the voice of the Dark Ages. That faint radio signal is our only direct link to the early universe, but it doesn't show us what the first objects looked like. For that, we need theory. And the leading theory has a name for that first generation of stars, Population 3, a name that marks their place in the sequence. Our Sun is Population 1, full of heavy elements. Older stars in the halo are Population 2, with fewer metals. Population 3 would be the originals, the first ones, formed only from the hydrogen and helium left by the Big Bang. That purity defined them. Without heavier elements to cool the gas, the physics pushed everything to extremes. These stars weren't like our Sun. They were likely monsters. Not 10 or 20 times the Sun's mass, but 100 times, maybe 200 or 300. A single Population 3 star could outshine a whole small galaxy of modern stars. They were titans born from the slow cooling of that primordial molecular hydrogen. Their formation was probably a solitary event. Deep in the gravity well of a mini-halo, one massive core would collapse. Not a cluster, but one dominant object, because the gas couldn't fragment. It all funneled into one central engine, so the first light to break the dark might have been a single, brilliant beacon. A fierce blue-white point in an ocean of black. These stars lived fast. With that much mass, the pressures and temperatures in their cores were staggering. They burned through their fuel at a ferocious rate. A star like our Sun lives 10 billion years. A massive Population 3 star might have lasted only a few million. A cosmic blink, their entire lives were a short, violent sprint, and their deaths matched their births. Two primary fates waited. For the very largest ones, above maybe 250 solar masses, the end might have been a quiet collapse. The star's own gravity, after fusion stopped, could have been so strong it just imploded, directly into a black hole. No giant explosion, just a final, silent vanishing, leaving a gravitational pit. For slightly less massive giants, the end was not quiet at all. They would have died in supernova of unbelievable power, hypernova, far more energetic than anything we see now. And in that fury, they performed the universe's first great act of alchemy. For the first time, the nuclear furnaces in their cores and the violence of the explosions forged heavier elements. Carbon, oxygen, silicon, iron. The ash of these first stars was seeded into the surrounding gas. That's the transformative legacy of Population 3. They weren't just the end of the Dark Ages, they were the beginning of everything after. By polluting the pristine gas with the first metals, they changed the rules. The next generation of stars would form from this enriched material. They could be smaller, cooler, longer-lived, and around those stars, the first solid dust grains could form. The first planets became possible, so these theoretical giants, born alone and dying in cataclysm, set the stage for our universe. They were the violent, necessary parents of complexity. Their brief, brilliant light wrote the first chemical instructions into the cosmos, instructions that would eventually lead to rocks, oceans, and life. But to move from theory to fact, we need to find their descendants, or catch the echo they left behind. That first star was a universe-altering event. Its light did more than just push back the darkness. It carried a specific energy, an intense flood of ultraviolet radiation, and that radiation acted like a weapon against the Dark Ages themselves. When those high-energy photons streamed out from the star, they slammed into the neutral hydrogen atoms filling all of space. Each photon had enough punch to knock the electron clean off a hydrogen atom. That process is ionization. A neutral atom gets ripped apart into its charged pieces, a positive proton and a free electron. Wherever that starlight reached, it didn't just illuminate. It scorched. It transformed the cold, neutral fog into a hot, seething plasma of charged particles. So around each of those first massive stars, a bubble began to form. A sphere of clear, ionized gas. It expanded outwards into the neutral hydrogen like a blister in the cosmic fog. Inside that bubble, the universe was transparent again. Like it had been in the very beginning, but this transparency wasn't universal. It was local, a pocket of clarity carved out by a single, furious point of light. This was the beginning of the end for the Dark Ages. Astronomers call this the epoch of reionization. It wasn't a single, instantaneous flash. It was gradual. A patchwork burning. As more of these first-generation stars ignited, their individual ionized bubbles grew. They began to overlap, to merge, creating ever larger regions of clear space. The neutral hydrogen fog, which had blanketed the universe for hundreds of millions of years, was being systematically burned away, eroded by the collective glare of the first stars, and later by the fierce radiation from the first galaxies and quasars. You can think of a vast, frozen lake on a cold morning. The first star is like someone lighting a single blowtorch on the ice. It creates a small, melted puddle directly beneath it. As more people arrive with their torches, more puddles appear. The puddles grow, they start to connect. Slowly, the solid sheet of ice retreats, replaced by open water. That's reionization. The cosmic fog was the ice, the first starlight was the heat, and the open water is the transparent, ionized universe we live in now. This transformation was fundamental. It changed the rules. In a neutral universe, light from stars couldn't travel far. It was absorbed. But in an ionized universe, light could race across cosmic distances. So the end of the Dark Ages meant the universe finally became a place where light could tell its stories, where galaxies could see each other, where the cosmic web could be illuminated. That first light didn't just end the darkness, it built the stage upon which all the cosmic history that followed would play out. That first light was a catalyst. But its real power was influence. The early universe was a delicate system, and those first stars introduced a new force, feedback, the idea that an object doesn't just exist in its environment, it reshapes it. Their radiation, their stellar winds, their explosive deaths, all of it injected colossal energy and new materials into the surroundings. It created a self-regulating loop. It dictated the pace and pattern of everything that came after. Think of a forest fire. A lightning strike ignites a tree. The heat from that burning tree dries out the ones around it. The fire spreads, but as it burns, it consumes the fuel. The intense heat can create its own weather, sending embers ahead to start new fires. The scorched earth behind is left barren. The fire both promotes and suppresses further burning. It depends on location. It depends on timing. The first stars worked on a similar principle. Their ultraviolet radiation ionized hydrogen. It also heated the gas around them. Hot gas has high pressure. It wants to expand. So around each massive star, you'd get this growing bubble. A bubble of hot, ionized plasma, pushing against the cooler, neutral gas outside. That pushing could do two opposite things. In some cases, it could sweep up a dense shell of gas at the bubble's edge, like a snowplow piling up snow. That compressed shell could become unstable. It could fragment. It could collapse under its own gravity. That would trigger a second wave of star formation right at the boundary. The first star literally builds the nursery for the next ones, but in other scenarios the effect was destructive. If the radiation was too intense or the gas too thin, that heating could just blow the raw material away. It could disperse the cloud, prevent it from ever cooling and collapsing again. A single massive star could sterilize its own neighborhood for millions of years. That's the dual nature of feedback. It's creative and destructive, a governing hand. It prevents runaway growth. It introduces a rhythm. The ultimate feedback event was the supernova. When one of those first massive stars died, it didn't fade. It exploded. The blast wave would race outwards, plowing into the surrounding gas. This could compress distant clouds, jump-starting star formation far away. Or it could completely shred and vaporize any nearby clouds. And within that shockwave was the star's most profound legacy, the first heavy elements. Carbon, oxygen, silicon, iron, forged in the star's core and in the explosion itself, now scattered into space. This was the universe's first act of recycling. That pristine hydrogen and helium gas was now subtly polluted, and that pollution changed everything. Gas with even a tiny amount of these heavy elements can cool much more efficiently. Atoms like carbon and oxygen can radiate heat away in many more ways. This more efficient cooling lets gas clouds fragment into smaller, denser clumps. So the second generation of stars born from this enriched material could be smaller, more numerous, longer-lived. The feedback from the first stars didn't just clear space. It changed the very recipe for making stars. It set in motion the transition from isolated titans to crowded stellar cities. The universe was learning to build complexity. One explosive loop at a time. These models need evidence. We can't see that time directly, so astronomers look for clues in the light from later eras. They use the brightest beacons as backlights, as cosmic flashlights. The most powerful of these are quasars. A quasar is the bright core of a distant galaxy, powered by a supermassive black hole feeding on matter. That process releases a staggering amount of energy. A single quasar can outshine its entire host galaxy by 1,000 times. Its light is a continuous beam across many wavelengths. And that light travels billions of light years to reach us. On that journey, it passes through everything in its path, including the wisps of neutral hydrogen gas, the last remnants of that early fog. When the light arrives, astronomers don't just see a bright point. They break the light into a spectrum, a rainbow, and they look for dark lines, narrow gaps where specific colors are missing. These are absorption lines. They're the fingerprints of the gas in between. Each element absorbs light at specific wavelengths. Hydrogen has a signature in the ultraviolet. A series of lines called the Lyman series. The most famous is Lyman alpha. When they point powerful telescopes at a distant quasar, they see something. They don't see just one Lyman alpha line, they see a forest, a dense forest of thousands of absorption lines all stacked up. This is the Lyman alpha forest. It's a direct record of the fog. Each dark line is a single cloud or filament of neutral hydrogen the light passed through. The line's position in the spectrum tells us its distance. Because the universe is expanding, light from more distant gas is stretched more, shifting its line toward red. By mapping this forest, scientists can build a three-dimensional scan of the hydrogen along that line of sight. It's like an X-ray of the universe's structure, using the quasar as the light source. The pattern of the forest reveals the state of the universe at different times. As you look at lines from gas farther away from earlier times, the forest changes. Closer to us, the lines are fewer, more isolated. That tells us the gas is mostly ionized, the fog has cleared. But looking deeper into the past, the lines become thicker, more dense. They merge into what's called the Lyman alpha trough, a broad, dark region where the absorption is total. That indicates a time when the neutral hydrogen fog was still thick. The boundary between the clear forest and that dark trough is a marker. It's the final act of reionization. The moment the last patches of fog were burned away, by studying hundreds of these quasar spectra, astronomers can piece together a timeline. They can see how the fog thinned. They can estimate when the last neutral hydrogen regions disappeared, and they can infer the properties of the objects that provided the ionizing radiation. Were they numerous small galaxies or a few brilliant quasars? The pattern in the shadows holds the answer. So we may never get a direct photograph of those first stars, but we can see their legacy written in the shadows they helped erase. These studies are a form of cosmic archaeology. We dig not with shovels but with light, reading the stories written in absence, in the colors that went missing on a journey of 13 billion years. That ancient light from the cosmic dawn, it left more than just a temperature map. It has a signature in its polarization. Light is a wave. Normally, those waves vibrate in all directions. But when light scatters off particles like electrons in that early plasma, it can become polarized. The vibrations get aligned in one direction. So the cosmic microwave background light, when it was finally set free, it was imprinted with this polarization pattern. It's a faint whisper of direction across the whole sky, frozen in time. For decades, we've studied the primary pattern, which tells us about the universe at 380,000 years old. But there's a second layer, a later imprint that comes from the era of reionization, hundreds of millions of years later. The first stars and galaxies, they flooded space with ultraviolet light, and they reionized the hydrogen. That process created a new sea of free electrons. And the ancient CMB photons, on their long journey to us, they passed through this later electron fog, and they scattered one more time. That scattering imprinted a new polarization signal onto the light, much fainter. It's like finding a second set of notes written in the margin of an ancient manuscript by a later hand. This specific signal is called reionization B modes. They're a unique curl in the polarization pattern, distinct from the simpler patterns from the universe's infancy. Detecting these B modes is phenomenally difficult. Their signal is incredibly weak, buried in noise from our galaxy's dust and the instrument itself. But if we can map them, they become a direct probe of that adolescent universe. They can tell us not just when reionization happened, but how long it lasted. Was it a sudden, dramatic flash, like a cosmic switch was flipped? Or was it a slow, protracted dawn, with flickering lights appearing across the cosmos over a long period? The pattern of these B modes holds the answer. By measuring them, we can constrain the timeline. We can learn about the collective power of those first luminous objects. How many were there and how bright were they? This changes our view of the cosmic microwave background. It's no longer just a baby picture. It's a layered historical document. The first layer records the moment of birth, and the final, faintest layer, it records the turbulent adolescence when the first stars rebelled against the darkness and changed the universe forever. The mainstream story is compelling, but it might not be the only one. The long dark could have ended in stranger ways. What if dark matter did more than just provide gravity? Some physicists think certain dark matter particles could have decayed or annihilated each other, and if that happened, those processes would have released energy. Not light we can see, but radiation. This invisible energy could have warmed the primordial hydrogen gas long before the first stars. That early heating might have changed the timeline. It could have delayed the collapse of the first gas clouds, made them too puffy to form stars, or in another scenario, it might have provided just enough extra energy to kickstart reionization in pockets of the universe, a kind of cosmic preheater. So instead of a passive scaffold, dark matter becomes an active participant, whispering energy into the void, influencing when and where light first broke through. Then there's another curiosity. In the heart of some early galaxies, supermassive black holes. We see them billions of times the sun's mass, already fully formed when the universe was very young. How did they get so big so fast? One radical possibility is they didn't form from the collapse of the first stars. They might have formed directly from the collapse of immense clouds of primordial gas in those first dark matter halos, a direct collapse black hole. If such objects existed in the Dark Ages, their influence would have been catastrophic and brilliant. As gas spiraled into them, it would have created searing disks of material, blazing with light far more intense than any early star. These beacons could have been the primary engines of reionization in their regions, burning away the fog with ruthless efficiency. These alternative pathways aren't the leading narrative. The evidence still strongly points to massive population 3 stars as the primary end of the darkness. But these speculations are vital. They're pressure tests for our models. They force us to ask harder questions about the clues we have. They highlight the gaps in our knowledge about how the dark universe and the visible universe spoke to each other. In that first formative era, the takeaway isn't that our story is wrong. It's that the cosmos in its infancy might have had more than one way to turn on the lights. The silence of the Dark Ages may have been broken by a chorus of different voices, some we are only beginning to imagine. Magnetic fields are everywhere now. They shape galaxies, they guide cosmic rays, but where did they come from? That's the puzzle. Could they have been there from the start, even in the Dark Ages? The idea is primordial magnetic fields, a subtle force in that early darkness. They would have been incredibly weak, just seed fields, maybe from chaotic processes in the universe's first moments. The faintest whisper of a pattern. For most of the Dark Ages, their influence was nothing. Gravity overwhelmed everything, but then structure formed. Gas began to flow, and that faint whisper might have found its voice. The amplification could have started with the motions that built the first stars. As neutral hydrogen gas was pulled into dark matter halos, it didn't fall straight in. It swirled, it created turbulence, and when a magnetic field line is caught in a swirling fluid, it gets stretched. It gets twisted. Think of stretching a rubber band. The field lines are drawn out and strengthened. That process is a dynamo. It could have taken those weak primordial seeds and made them significant within the collapsing clouds, so by the time the first protostellar core was forming, a magnetic field might have been there, woven into the gas itself. What could it do? The effects would have been subtle but potentially decisive. First, it could have influenced how the gas fragmented. Magnetic fields create a stiffness, a resistance to motion across the field lines. In a cloud collapsing under gravity, this magnetic pressure could have worked against fragmentation. It might have helped channel more material toward a single, massive core. Instead of letting it split into many smaller ones, that could have reinforced the trend toward creating those monstrous population 3 stars. Second, magnetic fields can transport angular momentum. A collapsing cloud spins faster, like a figure skater pulling in their arms. If it spins too fast, it can fling material outward. It can stall the collapse. Magnetic fields can act as a brake, transferring that spin away from the central core, allowing it to keep contracting. That could have been a crucial hidden mechanism, enabling the first stars to form at all. And finally, when those first stars died in supernova, magnetic fields entangled in the explosion could have shaped the blast. They could have directed the outflow of heavy elements, funneling them in jets, confining them in bubbles, influencing how those first metals were scattered. That would have dictated the initial conditions for the second generation of stars, setting the chemical landscape of the early universe. The open question is scale. Were these fields strong enough to truly direct the narrative, or were they just a background murmur? Current simulations are just beginning to include this physics. The answers aren't clear yet. It's a fascinating possibility that the story of the first light isn't just about gravity and thermodynamics. It's also about magnetism. An invisible hand from the dawn of time, gently guiding the birth of the first fires in the dark. The first light might not have been a star, not in the way we think of them. There's this idea, dark stars, a star that's dark. It comes from a certain kind of dark matter. If some dark matter particles were their own antimatter, they'd annihilate when they touched. Turn mass straight into energy, more efficient than fusion. So picture one of those early clouds of hydrogen. It's sitting in a dark matter halo, a dense one. As the gas cloud collapses, it drags the dark matter with it, packs it into the core, and there the particles start colliding, annihilating. They release energy. Heat and light. That energy pushes back against gravity, holds the cloud up, creates a balance, not a fusion star, an annihilation star, a dark star. These things would be enormous, puffy, millions of times wider than the sun, but cool, invisible to our eyes. They'd glow with a soft red warmth, and they could last for millions of years. Billions burning dark matter slowly. Their light would be the first, but it would be a dim dawn, a faint red glow, not ending the dark ages with a flash, extending them with a twilight. It's just a hypothesis. It needs a very specific dark matter particle and a dense enough halo. No evidence yet, but it makes you think. The first luminous objects might have been alien, not short-lived blue giants, but slow, huge embers, powered by the invisible stuff. Their end is another question. When the dark matter fuel ran out, the support would go. That huge ball of hydrogen would collapse. That collapse might set off a colossal burst of fusion. A supernova beyond scale, or it might just fall straight into a massive black hole. The dark star idea, it's a reminder, the story of the first light isn't finished. Our models are guides. The early cosmos might have been even more inventive. That final, fundamental change was the gas between the stars transforming. The intergalactic medium, that vast cosmic sea filling the emptiness, it holds the complete history of that whole era. For hundreds of millions of years, it was just a cold, neutral blanket. A simple shroud of hydrogen and helium atoms, drifting there in the dark, absorbing any stray light. That was the Dark Ages. Then the first points of light ignited, and their radiation began to work on that sea. The ultraviolet photons from those massive first stars, they didn't just travel, they acted like a chemical solvent. Where they struck, they ripped electrons from the hydrogen atoms. They heated the gas. They changed its state from neutral to ionized. This process, reionization, it didn't happen all at once. It was a slow patchwork burning. You can think of a vast frozen lake at the first thaw. The sun doesn't melt the entire surface instantly. Small puddles appear first. Around the warmest spots where the sun's rays are most direct, these puddles grow. They start to connect, channels form between them. Eventually, the solid sheet of ice is gone, replaced entirely by open water. The early universe underwent a similar transformation. Each of the first stars, and later each of the first galaxies, they acted as a local heat source. Around each one, a bubble of hot, ionized plasma began to expand into the surrounding neutral fog. These bubbles were the puddles. Inside them, the universe was transparent again. Light could travel freely, but outside, the neutral hydrogen still acted as an absorbing fog, keeping vast regions in darkness. Over time, as more sources switched on, these bubbles grew larger. They began to overlap and merge, creating ever larger clear regions within the neutral background. From a distance, the universe would have looked like a complex, three-dimensional Swiss cheese. A sponge of ionized cavities embedded within the last remnants of the neutral sea. This pattern wasn't random. It was a direct map, a record of where the first luminous objects were born and how powerful they were. A large, bright galaxy could carve out a huge bubble. A cluster of smaller stars might create a smaller, fainter one. The evolution of this medium, from a uniform neutral blanket to a frothy ionized foam, that's the most direct chronicle we have of the cosmic dawn's activity. It's a history written not in stone, but in the shifting state of hydrogen across the cosmos. By studying the final stages of this process, through the shadows in quasar light or the faint polarization in the cosmic background, we're reading that history backward. We're deciphering the story of how light fought its way out of the dark, one ionized bubble at a time. That final shift set everything in motion. The story doesn't end with the first light. It begins there. The decisions made in the dark ages, the properties of those first stars and the halos that birthed them, they echo forward. They're the foundational choices that shaped our entire cosmic neighborhood. So why does this ancient, dark era matter to us now, in a universe filled with brilliant galaxies? Because it wrote the opening lines of our own origin story. Consider the chemical legacy. Those first massive stars, the population 3 giants, they lived fast and died in supernova. In their violent ends, they performed the universe's first act of serious alchemy. For the first time, the furnaces of their cores and the shockwaves of their explosions forged elements heavier than hydrogen and helium. Carbon, oxygen, nitrogen, silicon, iron, the very stuff of rocks, air, and life. They scattered these first heavy elements, these first metals, into the surrounding gas. That was the crucial first pollution. It changed the universe's recipe forever. The next generation of stars formed from this slightly enriched material, because the gas could now cool more efficiently thanks to these new elements. Stars could be smaller, more stable, longer-lived, and around those smaller, cooler stars, solid dust grains could condense. Planets could form. Our solar system, our Earth, the iron in our blood, and the calcium in our bones, all of that material was forged in the hearts of stars that died long ago. The entire chemical pathway to complexity started with the ashes of those first, monstrous stars from the cosmic dawn. But it's not just chemistry. The large-scale architecture of today's universe was also drafted in the dark. The distribution of those first dark matter halos, the seeds that gravity nurtured during the dark ages, created a blueprint. That blueprint dictated where the first stars would ignite. And where those first stars lived and died, they enriched the gas. They influenced the formation of the next, larger structures. This process of hierarchical growth, small halos merging to form larger ones, pulling in gas and stars, eventually built the majestic galaxies we see today. The Milky Way's vast spiral arms, its central bulge, its surrounding halo of ancient stars, all of that can be traced back to the initial clustering of dark matter in the first few 100 million years. The Dark Ages set the initial conditions for galaxy assembly. The timing of the first star formation, the efficiency of that early feedback, it all cascaded forward. It influenced whether a region would become a dense galaxy cluster or a vast, empty void. So to truly understand a spiral galaxy like our own, you cannot start with the galaxy itself. You have to go back to the beginning. You have to understand the era of darkness that preceded it. Every mystery in modern cosmology, why galaxies have the masses they do, why they are distributed in a vast cosmic web, why they contain the mix of elements we observe, these are not separate puzzles. They are chapters in a single, continuous story that started before the first star ignited. By studying the Dark Ages, we are not just looking at a remote and empty past. We are reading the user manual for our universe. We are learning how the initial settings were configured, which ultimately allowed for galaxies, stars, planets, and the curious beings who now look back and wonder how it all began. The long night was not an empty interlude. It was the quiet, necessary prelude to everything. We have two ways to search for this time now. One is looking for the light that broke the darkness. The other is listening for the darkness itself. And these are the biggest astronomical projects we've ever tried. In space, there's the James Webb Space Telescope. It's our time machine. Its mirror is huge and coated in gold, built to catch the faintest infrared light from the very edge of time. It's not looking directly at the Dark Ages, but at what came right after. It's searching for the earliest galaxies, the first groups of stars that formed after those first giants. Webb stares into what looks like empty sky and finds these tiny red smudges. Galaxies so far away their light has been coming to us for over 13 billion years. They're the descendants of that first generation. By looking at their shapes, their colors, what they're made of, Webb can figure out the stars that built them. It can tell us how fast galaxies came together after the dawn began. And it might even see a group of stars that's almost pure, with hardly any heavy elements. A possible link back to that first, pristine generation. Webb is our view of the dawn's aftermath. On the ground, something completely different is being built. The Square Kilometre Array, the name means what it says. Its goal is a collecting area of 1 square kilometre, but it won't be one dish. It'll be a network of thousands of radio antennas spread across remote parts of South Africa and Australia. Its main job is to hear what Webb can't see, to tune into the 21-centimeter signal from the primordial hydrogen. The SKA will try to do what no telescope has done. It will map where the neutral hydrogen is across the sky at different frequencies, which means different depths in time. The goal is to make a three-dimensional movie of the universe from the middle of the Dark Ages, through the flickering start of the first stars, all the way to when the fog finally cleared during reionization. It will listen for the bubbles. It will chart how the ionized regions grew and merged. It will give us a direct count of the first luminous objects, not by their light, but by the shadows they left on the hydrogen around them. Together, these two form a partnership. Webb sees the fires, the SKA hears the smoke. Webb shows us the brilliant objects that ended the dark. The SKA shows us the vast, dark canvas they were painted on. One watches the actors, the other senses the stage itself changing. Their data will cross-check. They'll inform each other, making a picture that's far more complete than either could alone. If Webb finds galaxies formed earlier than we thought, the SKA should hear the hydrogen heating up earlier too. If the SKA finds reionization was surprisingly slow, Webb's count of early galaxies will tell us if there were enough of them to do it, or if we need stranger ideas. This attack from two sides is our best chance to turn the theory of the cosmic dawn into an observed history. We're not just imagining that long night anymore. We're building the instruments to finally see its end. Even with our best models and newest telescopes, some mysteries stay dark. That time before the first star is called the Dark Ages for a reason. We have a good story from physics and simulations, but the details are still shadows. We don't know the exact mass of those first stars. Were they 100 solar masses or 300? That difference changes their light, their lifespan, the chemistry they left behind. Simulations say they were giants, but nature could have been more inventive with a wider range of sizes than we predict. And the timeline is still a broad window. We say the first stars lit up between 100 and 200 million years after the Big Bang. But was it early in that window or late? And was it a single, sudden event in one spot, or a slow, patchy dawning across the cosmos? That answer tells us how quickly the universe woke up. Our observations point to a gradual process, but not a precise chronology. Then there are the wild cards, early black holes. Did supermassive black holes form straight from collapsing gas, skipping stars entirely? If they did, those primordial monsters would have been brilliant beacons. They could have dominated the reionization around them. Their influence might have been far more dramatic and localized than the collective glow of the first stars. We see fully formed giant black holes incredibly early, and their origin is a puzzle that points right back to the Dark Ages. Even reionization, which we map through shadows in quasar light, has an uncertain shape. We know the neutral fog was burned away, but what was the exact topology of that clearing? A smooth, advancing front, or a chaotic Swiss cheese of overlapping bubbles? Each model implies a different population of early light sources, and our current data can't choose decisively. And underpinning all of this is the biggest unknown, the true nature of dark matter. Our whole story rests on it providing the gravitational scaffolding for the first structures. But what if certain dark matter particles could interact with themselves or with the primordial gas? What if they decayed or annihilated, providing a subtle heat that warmed the universe long before any star? That single unknown could rewrite the timeline and the mechanics of the first collapse. Dark matter is the silent partner in this story, and we still don't know its voice. To acknowledge these gaps isn't an admission of failure. It's an act of intellectual honesty. It creates the most exciting map for future discovery. Every unanswered question is a coordinate, a destination for the next telescopes and theorists. The enduring darkness of this era isn't a void of knowledge, it's a frontier. It reminds us that the universe's first chapter is still being deciphered, word by faint word from the silence. That long silent time before the first star, it's a universe waiting, a cosmos of potential just sitting there, all the ingredients for every galaxy, every planet, every living thing they were already present. But it was just a simple, neutral fog, a universe that held the possibility of everything but the reality of nothing. That might be the most profound part. It was a blank canvas, but it already held the complete palette for all of creation. To think about that deep, unbroken quiet is to face a humbling perspective on our own moment. For hundreds of millions of years, the universe had no point of light, no complex structure. The drama of stars and galaxies, the chemistry of planets, the phenomenon of life, all of that was still a latent idea. A future chapter written in hydrogen and gravity. We, as conscious observers, we come from that long incubation. Our existence isn't an inevitable feature. It's a late arrival to a party that started in profound darkness. That realization shifts things. It asks us to see our sun, our planet, ourselves, not as central to the story, but as a specific and delicate outcome. One possible thread woven from a tapestry of potential, a tapestry set up during that ancient night. The Dark Ages tell us that complexity and consciousness aren't the default. Their achievements, their stories that needed time, specific conditions, a sequence of events that began with the simplest of beginnings. This era shows a fundamental truth, that vast, quiet periods of potential are often the necessary precursors to bursts of creativity and change in the life of a cosmos or in our own lives. It reframes darkness not as an emptiness but as a fertile ground, a necessary pause, a gathering of breath before a symphony begins. When we look up at the star-filled sky today, we're seeing the aftermath of that long gestation. We are the universe grown old enough and complex enough to look back, to wonder about its own silent childhood, and in that wondering we find a connection. A connection to the deepest past, a shared origin in a time of pure possibility where every future, including our own, was just beginning to stir, showing a time that left no direct image. That's the challenge. Science communication has to translate this abstract era, this data-rich period, into something people can feel, something they can see. So scientists and artists, they form a partnership, a unique one. They work to visualize the unseeable. They take the outputs from those supercomputer simulations, the immense ones, and animators, graphic designers, they craft visual journeys from it. They take the raw data, the positions of trillions of dark matter particles, the flow of gas, the ignition of the first protostar, and they give it form. They give it light and motion. What emerges isn't a photograph, it's a story, a scientifically informed story, the cosmic web materializing like a ghostly lattice in the void. Dark matter halos glowing as gravitational anchors, and that first point of fusion, that brilliant point bursting into being. These visualizations, they're careful interpretations. The colors are chosen for clarity, not because the early universe was violet and gold. The speed is accelerated by billions of times, but the underlying physics is respected. Meticulously, they are our best guess, rendered with artistic license to guide the intuition. This collaborative work finds its home in planetarium domes. In documentary films, in a dark planetarium, the audience doesn't just learn about the dark ages, they are enveloped by them. The dome becomes the early universe. You watch the cosmic web weave itself around you. You see the first stars ignite, like distant matches in a colossal dark room, and you witness the ionized bubbles begin to merge. It's an immersive experience. It bypasses the equations. It speaks directly to a sense of wonder. Interactive websites, museum exhibits, they take this further. They allow users to manipulate time, to zoom in on a collapsing cloud, or to follow the life cycle of a single massive star, from birth to supernova. These tools, they democratize cosmic history. They translate the complex language of astrophysics into a universal visual narrative. They allow a child, a student, a curious adult to grasp the monumental scale. The profound quiet of that era, this outreach is more than spectacle. It's a vital bridge. It connects the cutting-edge research, the work happening at supercomputers and radio arrays. It connects that with the public imagination. By making the invisible chapter visible, these creative endeavors remind us the story of the cosmos belongs to everyone. They transform data into discovery. They turn theory into a shared journey, back to the beginning of everything. That hum from the beginning of time is a ghost. To hear it, you need a silence that doesn't exist anymore, not naturally. So astronomers don't just build telescopes, they build sanctuaries, places where the modern world is held back. On purpose, so the ancient universe can finally speak. These are radio quiet zones. They're the only chance we have to listen. That 21-centimeter whisper from the first hydrogen is incredibly weak. It's not a broadcast, it's a background murmur, a temperature difference so slight it's almost nothing. But our civilization is a constant roar. Every cell tower, every TV transmitter, every satellite overhead. Even a spark plug in a distant car, they all flood the air with radio waves, millions of times stronger, billions of times stronger than the cosmic signal we're looking for. It's the ultimate needle in a haystack, except the haystack is on fire and screaming. You can't find the needle by adding more hay. You have to put out the fire. You have to ask for absolute quiet. So the most ambitious radio telescopes go to the most remote places. One of the most protected is in Western Australia. The Murchison Radio Astronomy Observatory. The land is ancient, red, vast, the human population is sparse, but that's not enough. Around the observatory, there's a legally protected zone. A radio quiet zone. It spans a radius of over 260 kilometers. The rules there are strict and simple. No cell phone service, no ordinary TV or radio broadcasts. Things like Wi-Fi routers or digital cameras have to be specially modified, or they're prohibited outright. The local community is small, but they've made a choice. They agreed to forego certain modern things, to live without standard mobile coverage, to protect this window on the sky. It's a quiet pact with the cosmos. The telescopes themselves don't look like classic dishes. The precursor there, the Murchison Widefield Array, is a forest of spider-like antennas. They sit low to the red Earth. They listen to the entire sky, not a single point. Their design minimizes electronic noise, their own noise. The goal is to become as passive as the landscape. To be a receiver, not a source, every piece of equipment is shielded. Every researcher visit is planned. A single unauthorized device could contaminate months of data. Something as simple as a smartphone brought too close by accident, it could paint a false signal across the sky, mimicking the very dawn we're trying to hear. This effort turns these remote deserts into something else. They're not just empty spaces, they're portals. By carving out islands of technological silence on Earth, we create a channel to the past. We turn down the volume of our own time to hear the faint echo of another. The sacrifice it requires, the cooperation from scientists, governments, local communities, it underscores something. The quest to understand our cosmic origins is a shared human endeavor. It asks us to be quiet, to be patient, and to listen together for a story that began long before the first word was ever spoken. The silence of the Dark Ages, it echoes through more than one field. To understand an era with no light, you can't just use a telescope, you need a coalition. Different minds speaking different scientific languages, and this draws its strength from a convergence. Cosmology, particle physics, chemistry, they're not separate stories here. They're chapters in one investigation. Each one holds a different piece, and the full picture, that ancient darkness, it only starts to emerge when they fit together. Cosmologists provide the stage, the timeline. Their work is the grand architecture, space and time. They study the expansion, the growth of structure from those initial ripples. They use tools, the cosmic microwave background, Baryon acoustic oscillations, to map the conditions before the first star. They ask the big questions. How fast was the universe expanding then? How did the gravitational pull of dark matter shape those first gas clouds? Their models give us the canvas. The vast, empty theater where the drama would unfold. Then the particle physicists. Their focus is the invisible actors. Dark matter is their domain. The nature of this substance, it makes up most of the mass in the universe. It's one of the greatest open questions. The properties of those particles, whether they're cold or warm, whether they interact, that directly influences how the first structures formed. Did certain particles decay, provide a subtle heat? Could they have annihilated, released energy that warmed the primordial gas? By running simulations with different dark matter models, they test their theories against the cosmic structures we see now. The Dark Ages become a laboratory, a 13-billion-year-old experiment. Its results are written in the distribution of galaxies today. So a question about the beginning, it helps constrain the fundamental ingredients of reality. And then there's the chemistry. It seems out of place in that vast emptiness, but it's central. The first chemical reactions were simple but monumental. The formation of that first molecular hydrogen, H2, in the cold, diffuse gas, it was a slow process. Fragile, computational chemists and astrophysicists, they model these reactions. They calculate the rates, how atoms could meet and bond with no dust, no solid surfaces. They study how these first molecules cooled the gas, let it collapse. This is chemistry under extreme conditions, low density, near absolute zero, and yet under the immense pressure of gravitational collapse. Understanding this primordial astrochemistry, it tells us how the universe built its first cooling systems. The essential step, the step that let gravity finally ignite the first fires. This interdisciplinary dialogue, it's what makes the study so powerful. A cosmologist's model of halo formation informs a chemist's simulation of molecular formation inside that halo. The chemist's results on cooling rates then tell the cosmologist how fast a star can form. And the particle physicist's model of dark matter properties, it changes the initial conditions for both of them. It's a constant, looping conversation. Data from one field validates or challenges the theories of another. So this isn't just astronomy looking back. It's a unified endeavor. It shows how a single mystery about our origins can be a focal point, bringing together experts who might otherwise never speak the same language. They're all reading different parts of the same ancient manuscript. One deciphers the handwriting. Another analyzes the ink. A third studies the parchment itself. Only together can they understand the story written in the dark. The word dark can be misleading. It might sound like a time when nothing happened, a cosmic slump, but in astronomy, dark has a specific meaning. It just means there were no sources of visible light. No stars, no galaxies shining, that's all it is. It's a description of the sky, not a description of the activity inside it. To call it an age of stagnation would be wrong. It was actually one of the most dynamic chapters, one of the most formative. The darkness wasn't an emptiness, it was a construction site, a silent workshop. The blueprints for everything we see today were being drawn up there, assembled. Imagine a vast forest at night. You see no movement, no color, but beneath the soil, roots are spreading. Seeds are germinating, life is preparing for the dawn. The Dark Ages were that hidden growth period. Gravitational forces were at work, sculpting the invisible skeleton of the cosmic web. The first simple molecules were learning to form, setting the stage for future chemistry. Vast rivers of gas were flowing, pooling into the cradles of future stars. It was a universe of immense change, purposeful change, all conducted in the quiet before the first note of light. So we have to reframe our thinking. The darkness wasn't a void to be filled. It was the necessary condition for creation, a period of gathering potential. Every action was a preparation. A preparation for the brilliant symphony to come. Appreciating this active nature is key. It transforms the Dark Ages. It turns them from a blank page in the cosmic story into its most crucial opening paragraph. That ancient construction site is quiet, but not for long. This time it won't be a star that breaks the silence. It'll be a flood of data. We're at the start of a new kind of dawn, a discovery dawn. The next 10 years, they're going to change how we see the cosmic Dark Ages. Right now it's elegant theory. Soon it'll be observed history. The tools are in place, or they will be. Tools to finally listen to that era, to see what came right after with a clarity we've never had. The James Webb Space Telescope is already rewriting the opening chapters. Its deep infrared gaze is finding galaxies, galaxies from when the universe was just a few 100 million years old. These aren't the first stars, they're the first cities built from their ashes. In the next decade, Webb will move from finding a few astonishingly early galaxies to building a real statistical sample. We'll learn their true numbers, their sizes, their chemical compositions. This census will tell us, indirectly, about the generation that came before. If we find many small, pristine galaxies early on, that suggests the first stars were numerous, spread out. If we find a few massive, already enriched ones, that points to a more dramatic beginning. A top-heavy start. Webb's data will constrain the timeline. It'll force our simulations to match a real, observed universe. Meanwhile, on the ground, the Square Kilometre Array begins its task. Its monumental task of listening, its primary goal is to map the 21-centimeter signal across cosmic time. The ambition is staggering, to produce a three-dimensional film of the universe's adolescence. A clear detection of the Dark Ages signal is still a monumental challenge, but the SKA's first decade should give us something profound, a much sharper map of the epoch of reionization. We will see in radio light how the bubbles of ionized gas grew, how they merged. We'll pinpoint when this process peaked, how long it lasted. This map will be the ultimate test for our theories. Does the pattern of clearing match where Webb sees the most early galaxies, or will there be a mismatch, a hint of other, unseen sources of energy, maybe those early black holes? Or something exotic in the dark matter? The synergy between these giants will be the engine of discovery. It's a conversation across the spectrum. Webb sees the fires. The SKA senses the smoke clearing. When their datasets are combined, we'll have our first true portrait of the cosmic dawn, a multi-messenger portrait. We'll move from asking what might have happened to describing what did happen. We'll know the sequence. Did galaxy formation drive reionization, or did early reionization suppress galaxy formation in certain regions? The data will tell a story with a beginning, a middle, and an end. And perhaps if the radio quiet zones are silent enough, if our signal processing is clever enough, we might catch that most elusive whisper. The 21-centimeter hum from the heart of the Dark Ages themselves, from before the first star flickered. Even a tentative hint of that signal would be a revelation. A Nobel-worthy revelation, a direct line back to the era of pure potential. This coming decade is a fundamental shift. For the first time, we're not just theorizing about the universe's childhood from its adult features. We're building the instruments to take its baby pictures. The long night that preceded all light is finally, after 13.8 billion years, coming into view. What we learn won't just fill in a blank page in a textbook. It will define the origin story, the origin of structure, of complexity, of our own place in a cosmos that spent its infancy in profound and creative darkness. That foundational story is ours now. The cosmic Dark Ages, it's not just some distant scientific question. It's the origin story of structure. Every spiral galaxy, every rocky planet, every element life needs, it all traces back to that silent workshop. To that time of pure potential, where gravity wrote the first instructions in the language of dark matter, and a fragile molecule of hydrogen learned how to cool a cloud, how to surrender to collapse. That long night wasn't an empty interlude, it was a necessary gestation, the universe gathering its breath before the brilliant, chaotic symphony of light began. We are the inheritors of that ancient darkness. The iron in our blood was forged in the heart of a massive star, and that star couldn't have existed without the unique conditions of the primordial cosmos. The carbon in our cells is recycled ash from those first, short-lived giants. Even the transparent space between galaxies, the space that lets their light reach us, that's a legacy of that era's end. When the first stars burned away the neutral fog, they built the very stage, the stage where the cosmic drama could unfold and be witnessed. Now we're building the instruments to witness its beginning. Telescopes like the James Webb Space Telescope, the future Square Kilometre Array, they're more than tools, they're time machines. They let us read that first chapter not as a theoretical sketch, but as an observed history. We're moving from imagining the dawn to charting its progress, from speculating about the first light to mapping the shadows it left behind. We stand on the threshold of turning this profound mystery into a documented chronicle. This journey reminds us our existence is a specific, delicate outcome in a vast cosmos. It asks us to look up at the star-filled sky with new understanding. To see not just points of light, but the brilliant, violent descendants of a first generation born from the dark. Every time we wonder about our place in the universe, we're engaging in a conversation that started over 13 billion years ago. In an era of profound quiet and immense creative power,